So for those of you who haven't met me, I'm Edmund Noble. I'll be giving this talk right now about which use cases you really have for data and which are just kind of vestigial from the object-oriented days. So some background about me. I maintain CATS, CATS-MTL, a recently split module of CATS dealing with composing applicative and monadic types, and F, which is also a project for composing applicative and monadic types. I contribute to Scala Z as well, and I work at Slam Data, where we're doing some awesome PureFP database and compiler stuff. So you can come by Gitter and say hi. I'm there all the time, way more than I should be, especially in the CATS and Scala channels. So specifically, this talk is about when and when not to use data in Scala, specifically how it's going to interact with the design of your programs and the performance of your programs. We're going to look at some functions that produce and consume data and discuss some different perspectives on those data types in different paradigms. Also, I apologize in advance. I'm probably not going to exhaust all of the time. This is a really long slot. So there's a bit of a split going on in Scala, which you don't kind of see in other languages, between these two kinds of types, which are sort of open types, these interfaces and these classes, which you can say, okay, well, I'm going to declare another type, which is going to be a subtype of that type. And then these closed types, these sealed traits, which you can't extend at all, also known as data types. In pure functional programming, the distinction isn't as obvious, especially in lazy functional programming, where everything kind of has a function or a thunk inside of it. So the openness or closedness of the type isn't really that important to this talk in particular, because it relates to subtyping, and subtyping isn't really that relevant to purely functional programming, except in some circumstances. So here's my take on what makes up a data type in Scala, and basically any other functional language. It's a sum of products. It's a sealed trait with several case classes, and these case classes are sort of branches of possibilities, and each of these case classes contains little bundles of data products. So sometimes these data types are going to be recursive, and that's mostly what I'm going to be focusing on here, because when it comes to performance, your asymptotic factors are going to depend on how often you're going to traverse your recursive data structures. So I'm going to cover some, a very basic type in Scala that everyone's used at least once. Either. So either is great for describing computations that can fail. The type on the left being the failure description, and the type on the right being the data produced if the computation was successful. You can monadically compose these methods that return either with the same error type, but you don't always have that. And that's kind of a barrier to compositionality a lot of the time. I don't know how many of you have come up with, domain, either you just use either of throwable, which is very common, or you come up with very module-specific error types, which are just composed out of smaller error types. Oh, right. So we're going to work through a little problem, which is divide two numbers, and assuming that one of them is not 0, the divisor, we're going to take the logarithm of that. And then, of course, we are assuming that that is going to be greater than 0, because otherwise it's not valid. So we'll take a look at a fairly common approach, which is you come up with this little data type, something like divided by 0, which is like a single branch data type. There's only one possibility. The only thing you can put in there is an int, which is the dividend that you tried to divide by 0. So this is, in essence, this captures all of the information that you had at the point of failure, right? So then, I mean, you can kind of expect the implementation, but then you have this next implementation of log 10, log base 10, and it does what you'd expect as well. But neither of these have the same error type, right? So now we have a problem. We're going to have to compose these somehow. So there's actually 3 ways at least that you can do this. I'm going to cover, well, 3 ways with data that you can do this, and at least 5 ways in total. I'm going to cover the 3 ways first. So the first thing you can do, which is very common, is you come up with this module-specific kind of error type, which is, I'm going to come up with divided by 0 or no logarithm, kind of come up with branches which are equivalent to both of the error types which I'm trying to compose together. And just left map over the either. This is from cats, but if you haven't used cats, it would be .left .map. And you just extract the information and you put it back in. Boilerplate, right? No one likes this. This is terrible, especially because you're going to have to keep doing this the further up your program you travel, right? So most of the time, I mean, in this case, you have so much less code than you have error handling logic. It's barely even there. It's almost lost. And that nominal type that you have right there, divided by 0 or no logarithm, is really useless because all you care about is that you got a divided by 0 or there's no logarithm. You don't care that you have these certain branches with independent meanings. All you care about is that it's somehow composed of the 2 error types which you're using. So here's another one. You can declare your error type compositionally using some kind of generic sum type construction tool. So I'm using either here again, so this is 2 uses of either being mixed, but you can also use shapeless coproduct for this, and it's a very common use of that. So then all we need to do is kind of wrap all of these errors up in left and right. The problem, though, happens when you have code calling this, and it has a different combination of the same errors, right? So you have L1 either L2, and that really neatly fits into L1 either L2, either L3. You just wrap it in left, right? Otherwise, what you're doing is you're completely deconstructing your error type into the leaves, and then you're reconstructing it into a different arrangement. And that is really non-compositional, and if you try to avoid it, you're going to end up with modularity problems because now your error representations are coupled together in their ordering. So that's not great. So the next way you can do this, and this is basically the monad transformer approach, just kind of inlined. So what you say is, well, the first thing I'm going to try to do is divide these 2 numbers. And the second thing I'm going to try to do is find the logarithm, which means that I can always say, if I can return no logarithm, I know the division was successful, right? So the other approaches kind of destroy this information. They throw it away. This could be useful information depending on your domain, but it's also a type which restricts your implementation, which is in general a good thing, right? That's something you like if you have very strongly typed functional programming. So the problem with that, though, is that if this order changes, that change ripples through your entire program, because if your whole program is written this way, you're going to have to keep rearranging things over and over again. So that's not great, but all of these eithers in all 3 of these approaches are being constructed just to be deconstructed later. Okay, so that's kind of a common theme of data. That's what you do with data. You construct it and you deconstruct it later. That's the only thing you can do with it, actually, is inspect what's inside the data and then make something else out of it. So you can see that the first and second options are different from the last one because they call flat map, and flat map destroys information. Okay, it destroys type information specifically. If you have an f of A, you flatten this to an f of A. What you're doing is you're saying, I do not care about the separation between these 2 f's. So, for example, you have option of option, right? You have a sum of none. That case is being destroyed. It's being assimilated into the none case, right? You have a list of lists. You have sublists. The sublist structure is being destroyed, flattened into the list itself, the outer list. Even if you're flattening a future of future, a task of task, something like that, you're destroying the information that there's something inside there that you can block on. That's not the same as the outer context that you can block on. So yeah, that's something to keep in mind about monads. All right, so we're going to take a bit of a break from either for now, and we're going to talk about list, which is very exciting. But first I've got a bit of a detour, because this talk is really mostly about intermediate data structures, the kind that you're going to construct and destruct. And I mean, I don't know that many data structures which don't operate like this. There's a few though, like binary search trees, for example. If your data structure is actually an algorithm which is kind of frozen in place, that you're updating incrementally, that's an exception. But for now, we're going to take a look at an intermediate data structure from a project of mine, which is just a description of some basic instructions in the SVG kind of instruction set. So if you want to draw a shape, draw some text, right, those are instructions in SVG. And I was working on this project which converts SVG XML into Android and iOS view code. So this is not, it's very simple. It's a very simple data type. It's not recursive at all. It's just, the problem is that SVGs are not a single shape that you draw on the screen, right? An SVG is a sequence of shapes. Otherwise, you know, Wikipedia wouldn't use them. So there are a sequence of shapes drawn in a particular order. And what we'd like is some kind of recursive variation of this type, which captures the notion of draw this, then this, right? And then we need some kind of base case which says draw nothing, because that's the end, right? Because otherwise, if you have, okay, this instruction contains the next instruction, you're not going to terminate, right? So here we go. We can add that in, and then we have, you know, this little next field in every single one of the branches except for draw nothing, which is extra. And this should probably look familiar because essentially what I've just done is inlined list into the previous type, right? So we could just replace this type with a list of the earlier type, and what we get out of that is separation of concerns, right? Because we don't always want to be using that in the same way necessarily. Sometimes you might care that your SVG is non-empty, for example, and then you won't want a monoid, you'll want a semigroup, so you'll use non-empty list instead. And you can just swap that out, and code that operates on SVG instructions individually doesn't care, right? So this is just a simple sort of program in this SVG language composed out of these instructions. You know, draw the text, Scala World 2017, draw a little circle around it. You'll notice that what we've done basically is we've taken this instruction data type and we've extended it into this kind of program data type, which tells you how to compose these instructions together. So we can also get things like we can take two of these programs and we can perform one after the other, and that's just list concatenation. And we can take an instruction and make a program out of it, and that is just consing something with nil. Similarly to the either example, though, if we want to shove a sum somewhere in here in the sense of a choice between, oh, well, my program is made out of SVG instructions and also these instructions optionally, right? We can't do that. Or we're going to have the same conversion issue as we did last time, which we don't want to have. So we can't nest the types, though. There's no last option. There's no way to describe this in a way which does not destroy all of the information about this instruction and the type information that would tell you that this is 2 instructions long, that is. So here's an example of a consumer of this kind of program. It inspects an instruction, you know, it checks which branch of the sum it belongs to, pulls out all the components of the product, which is in that sum branch, and then it takes, the text, the X position, the Y position, creates a value from them, and then calls itself recursively and concatenates the results together. So this has a name that you may be familiar with if you have background in computer science, which is structural recursion. Right? Structural recursion is just you recurse on smaller parts of the data, and that's it. So there's a few similar issues here to either, which are more exacerbated by the fact that this is recursive. So we've only built this list to destroy it later, right? And that may not seem like a huge problem now, and it isn't. But the moment that you start to operate on this list in more sophisticated ways, you're going to regret the amount of garbage collection you're doing and the amount of traversals you're doing. So we can also construct composite information types using composite instruction types using either, similarly to how we did in the earlier example, but there's still the same boilerplate involved, and there's still the same kind of conceptual overhead, right? You still need to think about how to combine all of these things, and it's too much to think about, essentially, because it's mostly not relevant to your logic, right? Your logic is, I want to render this to a string and smash them all together. That's it. So let's look at a different example. Okay, we'll look at a data type for random access to some presumably very large string. Write and read are the operations that you'd support, as you'd expect. And there's a type parameter to indicate which type these operations return. But there's a problem. There's no way to do anything with the data that is emitted or that is read when you consume the read instruction, right? So you've emitted this instruction to read data, but there's nowhere for it to go. And the only place it could go is into a function which is going to produce something else. So the first thing you can try then is to include inside the instruction to read data what you want to do with that data. And so we'll parameterize it on that, right? So we'll add an extra function parameter to this read instruction. Right, so you probably already see the issue with this, and that's that if you pass me a random access value, I have no idea. If it's a read of something, I don't know what it is, that A. I have no idea, because it's not in the random access type. It's existential, in a sense. You can't see it. So what we need to do then is expose that information to the receiver of this value. So we need to add a type parameter to random access and then propagate the type parameter from read into that type parameter. So that looks like this. Right, and then, that's all very well and good. So now we have a type of instructions, right? We have instructions, just like we did with SVGs. We have a type of instructions. Now we want a type of programs. So it stands to reason that we can get by with something that's kind of similar to list. A program is going to be a sequence of instructions. So case by case, we can see that write's going to have an instruction added as a parameter, the next instruction, just like in SVG. Right? So yeah, that looks essentially exactly as you'd expect. So now we've said, okay, well, read isn't able to just make any old data out of a string. It has to make another instruction which we can continue the program with, right? So you'll notice that there's actually no way to talk about this program, to decompose this program, except through structural recursion, because you actually need the value you've calculated at a node in order to even calculate what the nodes below it are. And otherwise, there's no way to traverse those nodes below. So the only option you have here is structural recursion. And this will be important later. So this is all well and good, but we need an ending. Just like we had an ending for the SVG program, we need to end with nothing, in a sense. Except, in this case, we do need to emit some kind of data, because, otherwise there's no purpose in reading data if we're not going to be able to emit some. So we're going to add a kind of base case, which is emit some value. That's it. So it'll look like this. the end. So to tie it all together, we get something like that. So those of you who are familiar with the free monad will notice that I just inlined the free monad essentially into here, just like list is the free monoid, and I just inlined it into the SVG program. And the connection here is that converting between an instruction type and a program type means adding some notion of sequentiality. And sequentiality is one thing, but having data emitted from one instruction and consumed by and used to construct the rest of the program is something else entirely, and that's exactly what monads do. So sometimes you hear people reference dynamic recompilation as what monads do, and that's exactly what I'm doing here. You use the value at runtime in order to compile the rest of the tree that you're going to traverse. So here's a small sample program. It's written using free, and it just takes some data at an index in some chunk, and then it copies it over the data right after that. So it's just called a dupe. And then we have this very funky looking interpreter for it, which is purely functional, yay, and it interprets random access into a monad which has access to state, which would be the string that it's accessing, and it has the ability to raise an error because your index may not exist in the string. I'm going to include both producers and consumers of data types everywhere in this talk because you need to know how both are going to operate in order to understand when you need to use data types. We can also make composite kind of instruction types using this higher kinded either type, either k or coproduct k, cop k, which is used to say, okay, well, I have a random access, but I also have option, and I want to take both of those and put them into the same program so that I can halt anytime I want and not yield any value at all. So you can wrap everything in either k. That's going to be really boilerplatey, though, again, and it's also going to be not just boilerplatey, but conceptually there is overhead, especially when it comes to reordering these. So yeah, but even, again, repeatedly, we are creating a structure just to destroy it and via structural recursion, and we have, and that's the essence of what we're doing in all of these examples. So we've been taking this set of instructions and translating them to a sort of grammar of programs where the instructions are non-recursive data types and the programs are recursive data types. And what the program kind of operator does is it introduces some kind of connective node, like some kind of branching in a tree, which links all of these instructions together. And this is actually also the case for either. Because either monadic composition is just another kind of branch that you can use for this kind of control flow between instructions. But in either's case, this connective structure is destroyed immediately when it's created. Right? It's not even really created at all. It's just either is inspected. If it's left, you stop immediately. There's no more structure building that goes on. So let's look at solving some of the problems that came up earlier. We'll start with the multiple instruction type kind of problem, because this is practically a very common problem, especially when it comes to the free monad. So you have, we'll start with either. You can have this, you construct things with either as usual. Let me see. Yeah, there we go. So you construct things with either as usual, but what you do is you have a type class called inject, which tells you, okay, well, I can take this small error type and put it into this larger error type. And this, the caller of those two methods has its own inject type class instances, and it passes them down so that no one needs to choose a concrete error type until basically the end of the world. So you don't have to worry about, where's the error going to go? Yeah. So we've abstracted over the nesting of these eithers, and we've abstracted over which other types are also in this nested either. And all we need to know is that this composite error type contains every error type we care about injecting into it. That's all we need. So the caller gets to choose it, and the problem is solved, right? And you can do this also for free, and this is done all the time. You can use this inject k kind of type class, which says, okay, well, I have a random access, and I have a coproduct or either k of random access with option, and this will generically let me inject it into that larger coproduct, and that is exactly what you need. And it also abstracts over the way you've nested it sort of left and right inside this structure. And that inject also works, the lower kind of inject also works for SVG equivalently. So before we continue, we kind of have to ask a question. What are we doing with these data types? Why are data types so nice to work with? Why do people like data? Especially seeing as we're in Scala, and we're in a, it's a strict language, so we do pay a cost for all of our data. So coming from object-oriented perspective, why in the functional perspective do we like data? And the reasons, I think, are firstly, while we construct a data type or data structure, we know that's all we're doing. We're not doing anything else. We're not moving the playing field. We're not shifting the ground under us, in that we're not executing side effects. Right? We're not mutating anything. Nothing is happening that would happen when the data structure is consumed. As well, we're also sort of freeze-drying or dehydrating this call tree into dehydrating this call tree of a program which calls into an interface, which is what it's going to do later, and allowing just kind of arbitrary inspection and manipulation of that tree before those interface calls get made. So if you know about the visitor pattern in the common object-oriented parlance, all that does is it translates this data structure or object graph or whatever you want to call it into interface calls. That's all it does. And that seems like something you'd want to do in functional programming as well, right? So think about all the things you can do with values of a type, right? All you can do with them is observe the values inside, and the properties of the observations you make are limited by the values you're observing. So the observations of the type are limited. They're a type themselves, right? All they are is functions which consume that type. So for the rest of the talk, I'm going to generally assume that we're doing purely functional programming because side effects really screw this up. So the only thing you can do with data is make new data. That's it. So we can encapsulate this kind of thing in a function, right? You can see if you squint here that the first and second functions here are totally equivalent because all you can do with an int is call a function from int to a, right? That's all you can do with it. Consider it this way, right? If I need a piece of information from you, I can either ask you for it directly, tell you to describe it to me, or I can get you to agree to answer any question I have about that information, which a lot of the time is going to be more efficient, right? Because most of the time I don't need to know everything about this information that you're holding. And they're equivalent in a sense because one of the questions I can ask of you is, what is this piece of information? And if I do get the piece of information from you, I can ask those questions of myself. So these two things are the same, right? So let's try to take this further into my first example from earlier. If you want to divide two ints, right, and return either an int or an int as an error, then all you need to do is pass some functions which tell someone, well, if you have an error, pass an int into that function and give me the result. If you have a successful result, pass an int into that function, give me the result. So you can, this is just about as clean as the other version was. If you're familiar, you may have noticed that this is continuation passing style, essentially. The caller here specifies the type that divide returns. Divide has to be totally parametric over this type, because otherwise it's not equivalent to emitting this value, which is going to be deconstructed by the caller, right? So yeah, these functions are normally called continuations. That would be an error continuation, that would be a success continuation. And the reason why is because they govern how the program continues with the result of the function. So the caller controls the control flow. What we've done here is we've church encoded the either type. And there are two sum branches of the either type, so you need two continuations. And the constructor parameters of both of those branches are int. And so are the arguments of the continuation. So we haven't allocated an error type here, right? We don't have a case class divided by 0. Boilerplate's gone. And we don't have an allocation. We do have a function call, which could be just as bad, right? So, you know, it's not a panacea in this case, especially. And here's, you know, the log10 function. Fairly simple. It's exactly what you would expect. But the interesting part is the composed function that you get out of this, because all you do is you call divide with the arguments that you'd expect. You pass along your failure continuation, and then your result continuation, your success from divide, is a function which takes that result and calls log10 on it, right? So you can see that everything's been kind of inverted. And we're kind of in callback hell, right? As the Node.js developers like to say, we are going to be nesting our code to the right as far as it goes. And this has practical issues as well. I mean, the stack is not unlimited. This isn't Haskell. Well, it's not unlimited there either, but they don't really have a stack. But we can't just do this forever. This is going to have to terminate eventually. We can't do recursion this way, especially because the stack will definitely be blown. Secondly, performance, right? We have these function calls, and this is such a generic method, right? You could pass any continuation to this in any context, and that means that the JVM has no idea which function is actually going to be passed to it. And that means the JIT can't inline it, and that means that you're in performance hell, basically. What used to be somewhat fast is now even slower because there's some extra jumps in there which can't be inlined. It seems like there's some improvements we can make, in short, to this kind of style. There is actually an interesting proof, which I won't repeat here because there's plenty of people in the audience that you can and should annoy about this later, that continuation passing style is implemented by monads. They're actually equivalent in a sense. So you can avoid callback hell using for comprehensions. And that's generally the point of for comprehensions is I don't want to, for example, for option, I don't want to keep checking that something is none or pattern matching, nesting over to the right over and over again. What I want to do is say, okay, I've matched here and and if it's none, I've stopped. And now let's move on to the next thing. So all we need is a way to kind of inject our errors into a monad, and then we've already gotten rid of callback hell. It's gone. So we're going to do the simplest thing possible, which is pass around a monad instance to replace our result continuation. So we're going to use monad's pure method, which will take our value of type A and bring it into a value of type f of A. I'll be using cats here because this is what I'm familiar with. But so that's what it looks like. I'm still using continuations for the failure here because I'm assuming that there's no recursion that'll happen there. You don't have to. You can use a monad transformer type class like monad error, which is essentially like inject, but it also has the monad constraint added on it as well. So you can say, I'm going to raise this error into this monad, and you can pretend like there's a value of any type in here because there's actually an error, and you're not going to be able to inspect it anyway. Everything we have here is basically the same as what we had earlier, except there's less continuations. And there's some nice, the syntax is about as nice. We don't have any more insane boilerplate still. And what do we do about performance here? Because we are still probably, I mean, what monad are we going to be injecting to? Probably either. Probably over some large error type, which is the sum of all the error types in our program. And what do we do about performance? And the answer is basically nothing. There's nothing you can really do about either's performance. Either's performance is just limited by the JVM. That's essentially how it is. But that's because either, mostly, is because either is not recursive. Either is very simple. You can just match on it, you're done. If you've got some tree of height n, and you don't want to spend big O of n over and over and over again, then your techniques start to change, okay? So, yeah?
F of A, the last one, the return type of the last method, F of A?
Yes, that should be f of double, actually.
F of double.
Yes, yeah, thank you. So,
Just another question. Could you apply the monad error style to this last slide?
you could have, yes. Yeah, definitely. I would probably actually do that practically. I'm just trying to go with the most minimal change that kind of makes sense. So, let's talk about lists. Folding a list can be done two ways, right, from the left or from the right. And in order for both ways to have the same result, the folding function has to be associative, right? So, you know, it has to have the same properties as list concatenation does. They need to look the same in this kind of law. As well, lists have this empty value nil, which is the identity with respect to this list concatenation. And list concatenation, yeah, it's associative. So you can create singleton lists from single values, right? And let's say then that our goal is to fully church encode our list. What do we need to do that? Well, firstly, we need some way to ignore which association that the function, the continuation, is going to be called with. And secondly, what we're going to need is some kind of identity, some kind of nil, essentially, that will not change the result. So what do we need for this? We need exactly a monoid. That's all we need. And it's no more than we need either. Because list is a free monoid. So we have a church-encoded variation of our SVG data type, which is totally specified in terms of an interface now. So all of these are just functions which take these observable kind of products of data into this type A, so that it's a kind of observation of the SVG type. So that you don't construct it, all you do is you construct a tree of observations of this type. We don't have a program type here, though. We still have just an instruction type. We need a way to compose all of these, right? So our program type is actually a method type, which is interesting. I mean, method types don't come up a lot. The method type here would be, you know, for all A monoid, SVG, SVGA, blah, 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 returns A. So you can see that we have this monoid constraint here. So instead of earlier we had this list of SVG data type, right? We separated our concerns somewhat to the point where you don't have to use a list in order to use this SVG data type, but you probably will, practically, because most of your code is going to deal with this list of SVG. Now we have it's totally abstracted. Only the use site, only the program itself cares about the composition method. So this is even better separation of concerns. As well, since this works with an arbitrary monoid, you can see that we're kind of building this list, or not building the list. We're building the fold of the list directly. We're not building a list. So we've removed the monoid from consideration, and the structural recursion over the list. Now what we're going to do is we're going to inline it into the program's call tree. So we don't just have a better separation of concerns here. We have less allocations. We have a JVM interface that unlike in the case of those either continuations, is probably only going to be called with very few concrete interfaces, which means that the JIT will be able to inline it in most cases, which means you'll get much better performance. I benchmarked it. I promise it's fast. So this isn't even the biggest performance benefit, though, which is traversal, right? The bigger this list would have gotten, the bigger the cost would have been to traverse it over and over again, you know, following all of those pointers. So now what you can do is, if you have multiple of this kind of interpreter of the program, right, you can compose them into a single interpreter, which then requires only one pass over the entire call tree, in a sense. You only need to call you only need to call this once, but you can take products of monoids and you can take products of these SVG interpreters, and then all you have is one traversal. Okay, so let's look at what we're going to do with random access. So this is our church-encoded variation of random access. So now all we have is this interface, as usual, and it's returning something in F. Instead of having this case class, you know, extends random access of unit, we have write, which returns F of unit. And this makes sense because all you do with a free monad is you translate it into a concrete monad. Right, and instead, all we're doing here is eliminating the middleman, right? We're just directly creating things in a concrete monad. There's no structure to create, there's no structure to traverse or transform. So that's just as advantageous as earlier, except the free monad is way slower than a list. And you know, here's a similar version of dupe. You'll notice that there is no more free.liftf anywhere. There's even less boilerplate. So yeah, instead of constructing this frozen call tree and then traversing it to generate all these function calls with a visitor, we're just calling into the visitor directly, and that's all we need, because there's no side effects the visitor is going to produce that we're going to suddenly interrupt the traversal and do it out of order or something like that. So that's the advantage here with pure FP. So let's look at the church-encoded interpreter, which is the exact same as the other interpreter, except it has methods instead of case statements, and that's in general the difference between an interface and a data type. So all right, so I'm already basically done. So at the risk of sounding a bit presumptuous, you've probably noticed that all three of these examples I've leaned on have the exact same problems and the same solution. And so you may be wondering what kind of trade-offs we're incurring here in most of these cases, because you know there's never an amazingly easy answer in software. So as I mentioned earlier with either, if you're passing a lot of different functions around, you're going to incur the wrath of the JIT, and you don't want to do that, right? So in some cases, it is going to be better to use data, to traverse data, than it is going to be to directly construct the call tree. So yeah, in either's case, as I said, this is unavoidable. So the performance benefit isn't going to be is going to be negated, but in the other cases it's not, because the traversal becomes more expensive, and with free monads especially, it's very expensive. So it mostly builds up the more traversals you do and the more transformations you do on this data, especially if you're building a very modular functional application that's going to translate from SVG to draw something and then to Android code and then to string. You have these 4 layers, and if you have a large file, you do not want to have to traverse 4 times. It's untenable. And I've heard some examples of people who, especially in Scala.js, who will build up they'll parse a gigantic piece of JSON, and then they'll translate it into Circe's JSON representation, and then they'll translate it into their data, their model, and by that time, it's been around 5 seconds, and the user's mad. So that's a huge problem in JavaScript especially. So the reason behind this, this generally being a good idea, is that most of the time an intermediate data structure is only used at one kind of module boundary in your program, or maybe a few module boundaries simultaneously. And what that means is that the JIT will almost always be on your side, though you should still profile if you really care. So it's easy to use a single interpreter or a bundled interpreter of several interpreters. The cost of the traversal is by far the biggest issue. So avoiding this repeated traversal is very useful, especially with free, because you can do things like generate from one element of your free algebra an entire free monad out of it, and then you have to kind of collapse that into your outer free monad, and that's just terrible. Quadratic even. So when should you actually return a concrete recursive data type from a function? I've actually only come up with one example, which is data types with cycles, graphs, etc. Because, this will just infinitely recurse if you try to do this way. But otherwise, I can't think of a single good example. I mean, it depends. How far you're going to church encode it is going to depend. But in general, you want some kind of abstraction over the data you produce, because otherwise you get into this problem of converting between these data types, and it becomes more of a problem than your actual code does. As well, it's likely to be a performance advantage to do that, depending on how far you go. And this generalizes because you can always write implementations of interfaces that will generate a concrete data type that corresponds to that interface. That's always possible, and that is fundamentally. It's not even something about lambda calculus. It's something about category theory, which is just fundamental. So yeah, even if you do require this data later on, you can produce it and you can change your code very minimally. You can just add one type parameter, and boom, the entire thing is, not only do you not sacrifice you still avoid doing multiple traversals until you allocate the data structure. Then whatever you do from then on is still an extra traversal. So if you're going to require data, when do you actually require data? When do you want data as an input to a function? And there's a few cases where you may want that. Firstly, if you do primitive recursion. So primitive recursion is when you recurse arbitrarily deep into your data type before doing a recursive call. So you peel off as many layers as you want, then you do a recursive call. And that is a problem because what that means is you still need some kind of freeze-dried kind of representation of your call tree. And church encoding actually makes that n squared, which is, pretty terrible. As well, you also need to kind of store these call trees, these frozen call trees, as functions, which get composed with each other, and that's also terrible. So it's very slow. In general, structural recursion is the best thing to do with this kind of technique. If you're doing primitive recursion, just cut off your structural recursion boundary and just be like, I'm making data right now. Or, here's another way. Let's say you want to traverse data structures in a different order than you're constructing them. So if you want to fold a list from the left, if you really want to fold a list from the left, you should probably just build a list and then fold it. Because otherwise you're going to do some crazy reverse continuation building, and it's going to be really slow. Other than that, there's a few specific examples. Daniel Spivak has this mocking library which works with free monads, and it peels off layers of the free monad, and you can basically assert on it. It's like a mocking library for pure FP, and that requires that you have free. But you don't have to. You should still consume this interface from the function that produces free, but fix it as free in your tests. Only in your tests. That's the only place you need it. And some complicated tree rewrites also require concrete data types. When I say tree rewrites, I mean that this generalizes arbitrarily to any kind of recursive data structure that you're going to be using in your program. So if you're doing some kind of complicated rewrite that does like, I don't know, optimizations or something like that, that aren't just peephole optimizations, then you certainly want to allocate it. Almost certainly. You may be able to get around that if you try hard enough, but it'd be hard. So when in doubt, you should profile. But in general, you have two things on your side, right? You can always swap between data types and interfaces whenever you want. And if you do that, the rest of your code is totally insulated from that change. So you don't have a huge cost from doing this. If it turns out you want to back off, that's fine for the rest of your code. So this is the last slide, just a little bit of theory. So there's this adjunction in category theory between free functors and forgetful functors, which shows why church encoding works in not just any lambda calculus, but also in any Cartesian closed category. So I don't have a lot to say about this adjunction. Even if you don't know what an adjunction or free or forgetful functors are, church encoding is a concept with deep theoretical roots that go beyond computer science into category theory. And producing a concrete data structure is always possible to refactor into consuming an interface with the right type. And that's the essence of adjunction, right? You can make some modification to the input of your function, and it's the same thing as if you made a different modification to the output of your function. It's isomorphic in some sense. Yeah, that is all of my talk. Thanks. Questions? Yes?
Am I correct in thinking that the suggestion for what you described there with the track is the finally-tagless?
Yes, exactly. It is finally-tagless. It is a final algebra as opposed to the case class sealed trait thing, which is an initial algebra. Yes. Sorry?
In your final encoding, do you still have a problem of combining these, like if you have two algebras that are finally encoded, now you want to combine them in some way, you still have this problem of now you have to manage the functors that these algebras are encoded around?
So what you do is you take two of these algebras and you demand that both of them have the same type parameter, because then composition naturally falls out. Because in a sense, the caller has already dealt with it for you, right? So you can just kind of chain that up arbitrarily so that one person has to deal with this ever in your entire program. More questions? Yeah?
Can you go back to the slide with the inject type class?
Sure.
So I just wonder, the precondition is that if we have some nested headers that they don't contain the same type, right? So if I had like...
Exactly, yes.
So what would happen if they contain the same type? Would the inject type class not compile, or would it take the first one of them, or...?
I don't know. I mean, it could compile. It could give you an ambiguous implicit. I feel like it would just compile and inject into the first slot it finds. That seems like what would happen. Because in general, implicits don't backtrack that far, I don't think. But I may be wrong. I mean, we have some Scala compiler engineers somewhere here, so.
Is that from cats, the type class?
I do believe that cats has an inject type class, yes. Yes. Any more?
So, I understand free give you stack safety for your interpreter?
Yes. Oh, yes. Oh man, I should have mentioned that already. So the nice thing about free, as you say, is that free gives you stack safety in terms of your monad, even if your monad is not stack safe. So for example, I mean either or option, for example, if you call flat map, that's immediately going to try and evaluate that the value on the left that you're flat mapping over. Free doesn't do that. So you may be wondering then, why would it be safe in general to use this final tagless interface over a monad? And the answer to that in general is that most of the time, and in my experience all of the time, your monad is going to be, you're going to be chaining it through another final tagless interface, and you're chaining it through another one, and then the last one is in task or I/O or something like that. And task and I/O and those things, they're all free. They're all variations of free. So you still get the stack safety, but you only pay for it once. You don't have to pay for all the algebra allocation. You don't have to pay for the intermediate free monads or anything like that.
So you could require monad arc as a constraint?
That probably won't help because in general you can't, I don't believe you can eliminate all, I mean, you can't take all monadic recursion and make it into tail recursion. Just like you can't take all normal recursion and make it into normal tail recursion. So, yeah. But in that case, yes, you could, if you do want to do some tail recursion inside your monad, yes, totally require that instance on one of your methods, and or even in cats, they've folded it into monad itself, also has tail rec m. So yeah, you can definitely do that. Anyone else? No? All right. Well, thanks a lot.